Hello, welcome to the next section, Regularization for Database Improvement. In this section, we will introduce the idea of statistical regularization to improve data models in an effort to help comprehend what statistical regularization is. Now we move to the first video, Statistical Regularization. In this video, we're going to understand statistical regularization using data. The term regularization has been described as an abstract concept of management of complex systems. These rules will define how one can add or modify values in order to satisfy a requirement or solve a problem. Within the statistical community, the most popular statistical regularization methods may include ridge, lasso, and least angles. Ridge regression is a statistical technique that is used when analyzing regression data or models that suffer from a condition known as multicollinearity. When multicollinearity occurs, estimates may be unbiased, but their variances are usually large and far from the true value. This technique adds a degree of bias to the regression estimates to reduce standard errors. Lasso is a short form of least absolute shrinkage and selection operator. Lasso is a statistical technique that performs both variable selection and regularization in an effort to enhance prediction accuracies within a model. Least angle regression, or LARS, is a statistical technique used by data scientists when dealing with high-dimensional data. If there is speculation that a response variable is determined by a particular subset of predictors, then the LARS technique can help with determining which variables to include in the regression process. So, when would you consider using any type of regularization method? Well, the truth is that there is no absolute rule that dictates the use of regularization. However, there are certain indicators to observe that should cause you to consider regularization. For example, if your data contains a high variable count, if there is a low ratio of the number of observations to the number of variables in your data. When a data scientist speaks of high variable counts, they are really referring to an excessive number, or if the number of variables is approaching the number of observations. But suppose we had more than 50 possible predictor variables in our data of only 100 observations. This is what can be referred to as an overly complex model and warrants consideration of using a common regulation method. Regularization is the statistical technique used by data scientists to avoid or address this overfitting problem. The idea behind regularization is that models that overfit the data are complex statistical models that have, for example, too many parameters. Other known opportunities for the use of regulation includes instances involving high collinearity, when a project objective is a sparse solution, accounting for variables grouping in high-dimensional data and classification. Ridge regression is a statistical method that introduces a control to the model's regression estimates, but is effective at reducing the model's variance as well. There are a number of different R functions and packages that implement ridge regression, such as lm.ridge from the mass package and ridge from the genridge package. In section 6, Database Progression to Database Regression, we saw an example where we created a linear regression model on data from a consulting company's project results in an effort to predict a project's profitability. We will perform that once again. We use the R function, lm, to build linear regression model using all the project's results data. This code generated a linear model using our R object named myData, using the project management variable to predict profit. Now we are going to use the lm.ridge function in an attempt to acceptably fit the preceding linear model using ridge regression. This is the syntax for the same. Formula is a formula expression as for regression models of the form response, predictors. Data is an optional data frame in which to interpret the variables occurring in the formula. Subset is an expression saying which subset of the rows of the data should be used in the fit. All observations are included by default. na.action is used to filter missing data. Lambda is a scalar or vector of ridge constants. Then we need to know if should the model frame design matrix and response be returned. Contrasts is a list of contrasts to be used for some or all of the factor terms in the formula. We will now look at an example. We will first utilize the runIf and rnom functions to generate some random number datasets to be used for illustration. We will now see the difference between executing lm and lm.ridge. So first we create a uniform random number series as x1, x2 and x3. Then I create a new variable from x1 and x2. Finally, I create a random number EP using rnorm function. As we know what we want to explore, we can take liberties with creating the testing data. So we will see an example of R code that generates a linear regression model using our 3 made-up variables. So I use the rlm function to create an ordinary least squares. Running it gives me this result. Now let's move on. Using our same made-up example data and similar thinking, we can use the R function lm.ridge to attempt to fit our linear model using ridge regression. Before that, we need to install mass packages, so I add this line to install it. Then add this library method. Finally, I use the lmridge function and then use summary function. You'll find that the summary function does not yield the same output on a linear regression model as it does on a model using the ridge regression method. However, there are a variety of packages available to produce sufficient output on ridge regression models.